So the first thing that we're going to talk about today is the concept of effective values. So when we dealt with our power relationships in our last class meeting, we had big, ugly, terrifying equations, and so we're trying to figure out how to represent things without using big, ugly, terrifying equations. So I'm going to call this section effective values. For periodic waveforms. All right, so I'm going to attempt to draw a picture here, and as per usual, it will be terrible. So what I am attempting to draw is a standard receptacle that we might see here in the United States. For those of you that are not aware, receptacles are different shapes all around the world. So we might have something that looks like this. Okay. So for a standard receptacle in our homes, we have three prongs that we are able to plug into this receptacle. So let's talk about what those prongs are. This one at the bottom is our ground pin. Typically has a green wire. Then we have the large rectangular slot. This is our neutral connection. This guy was ground. And on the other side, I'm going to do it in gray, but it's typically a white wire. Is our hot wire. So I want to ask you guys what I hope is a straightforward question. What voltage is provided by a receptacle here in the United States? 120 volts. All right. So Walker says that the answer is 120 volts. He isn't wrong, but he also isn't right. So let me explain why. This was a trick question. You gave me the exact answer I was looking for, by the way. So is power distributed as an AC signal or a DC signal here in the States? AC. So how is it that you're representing a time varying voltage with a single number? You ever stop to think about that? Nope. Okay. Well, we're going to explain why it works that way right now, right? So Walker is absolutely right that we would call this conventionally 120 volts. I'm going to add something else here. I'm going to put a little RMS as a subscript, and we'll talk about what that means here shortly. So what this 120 volts RMS is an effective value for a time varying voltage, V of t, where V of t is equal to about 169 volts and some change, cosine 120 pi t plus some particular phase angle that depends on when we start measuring things. And that 169 is approximate, so I'm going to put this here. So now we're going to talk about how in the world we get from this representation of a big, ugly time domain function to this representation that looks effectively as if it were a DC voltage. Okay. So we're going to define an effective value. So effective values are the DC equivalent voltage or current that delivers the exact same average power as, excuse me, not at, V of t, or in the case of a current, I of t, to an arbitrary load. So we have a statement here that's telling us what's going on. Because we're engineers, let's throw some math at this and figure things out. Okay. So if I have a DC circuit, what are my relationships for the power delivered to a resistor? I have two of them, right? I could have the, let's say, P average could be written as my DC voltage squared divided by my resistance value. Or my average power could be written as my DC current squared times my resistor value. When we're in a DC circuit, the average power is the exact same thing as the instantaneous power because it's a constant, right? So we don't have to really think about things too terribly much. Now for an AC system, the average power provided to a resistor in terms of the voltage would be the integral over one period of our AC voltage squared divided by our resistance value with respect to time. And in terms of current, we would have almost the exact same thing, except that we would have R times I squared. So what I'm going to be doing is I'm simply going to set the DC average power relationship equal to the AC average power relationship, and then solve for VDC and IDC respectively, because that'll give me the DC equivalent voltage and DC equivalent current that are providing the exact same amount of average power as our periodic signal is. So for voltages, we would have the relationship VDC squared divided by R is equal to 1 over the period times the integral over one period of our periodic voltage signal squared divided by R dt. We can notice that there's a factor of 1 over R on both the left-hand side and the right-hand side of the equal sign. So the resistor value that we're delivering average power to doesn't actually matter at all. And so now to just get VDC, I'm simply going to take the square root of both sides. And I'm going to change the label of VDC to be V effective. Okay. So the effective value for my voltage will be the square root of 1 over t times the integral from 0 to t of the periodic voltage waveform squared with respect to time. I can do something very similar for currents. So I can say that my DC current squared times R is equal to 1 over capital T times the integral over one period of R times I squared of T dt. Once again, I have a common factor of R on both sides, so I can throw it away. Taking the square root of both sides then gives me my expression for my effective current. And it is literally the exact same relationship, except that I'm replacing V with I. So now let's talk about those three little letters, RMS. So up here, I said that the effective value for the voltage that's being provided by one of the receptacles here in the United States was 120 volts RMS. That subscript RMS stands for root mean square. And we use that to let us know that we are taking or dealing with effective values, because the mathematical operations involved in calculating the effective value is we take the square root of the arithmetic mean, that's just a fancy word for average, of the square of our function. So we're literally doing the root mean square of the voltage in order to get the RMS value or the effective value of that voltage. Okay. So that's what RMS means. Anytime you're given a voltage that has units of volts RMS or a current that has units of amps RMS, you're already dealing with the RMS values or the effective values for voltage and current. If you're given volts, you may need to convert to effective values depending on what operations you're trying to do. And we'll talk about that quite a bit in maybe 20 minutes or so. But before we get into where we use this, which is complex power relationships, let's look at a couple of examples and apply this relationship. So let's say that I have the following voltage waveform. So this is going to be V of t. Here's time measured in t. And I want a train of rectangular pulses. Where the maximum value of this guy is V naught. Let's call this point in time capital T. And the way that I've drawn this, my voltage waveform is on half the time and off half the time. This is what we would call a 50% duty cycle. Some of you might have noticed it says duty cycle on the function generators when you're playing around with a couple of the settings and all of that kind of stuff. So instead of saying that this is just a generic 50% duty cycle, I'm going to call this point in time x of t, where x is a number between 0 is less than x is less than 1, and it represents the duty cycle for this signal. So if x were 0.9, then 90% of the time our signal would be at V naught. The other 10% of the time it would be at 0 volts. If our duty cycle were 25%, 1/4 of the time our voltage would be at its peak value, and then the other 3/4 of the time our voltage would be off. 50% of the time we have just simple rectangular pulses where half the time it's on, half the time it's off. Okay. So we could mathematically describe our periodic voltage waveform over one period as a piecewise function where we have a value of V naught for 0 is less than x times capital T, and we have a value of 0 volts for x of t is less than t is less than capital T. So in order to find the effective value, I'm going to apply my equation. So that's the square root of 1 over capital T times the integral from 0 to capital T of my voltage waveform squared with respect to time. And now I'm going to put in the parameters for this specific voltage, right? So my period is still just labeled as capital T, so I can leave that alone. Because I have a piecewise function, I'm going to integrate from or over that one full period by breaking that integral up into smaller parts, right? So I'm going to have one part that goes from 0 to x times capital T. My voltage over this interval is just V naught, square it, dt. And then my second integral is going to be from x sub t all the way out to capital T. My voltage is 0, square that. So overall, I've integrated over exactly one period, which is what I'm supposed to do. But because I had a piecewise function, I had to break it up into smaller parts, right? All right, so let's start with the easy part. What's the integral of 0 squared? 0. So we know for sure that this part goes away. What's the integral of V naught squared going to be? So V naught doesn't depend on time at all, so we could actually take that out, right? So we could say that our effective value would be the square root of 1 over t times V naught squared times the integral from 0 to x of t of just dt, like so, which is just going to look like x sub t, right? So it's going to be the square root of 1 over t times V naught squared times x t. These t's cancel each other out. And what we wind up getting is simply V naught times the square root of our duty cycle. So that is the effective value. Let's now look at something a little different. Yes, ma'am. Repeat your question. So we're looking at it over exactly one cycle. So my integration was carried out from this point in time to that point in time. Yep. So I integrated over exactly one full cycle. Yeah. Any other questions before we move on to another example? All right. So let's say we have another voltage. This time, here. I want to find out what the effective value for what we would commonly call a sawtooth wave is. Okay. Where the maximum value of this thing, we'll still call that V naught. And we can see that this thing repeats itself every capital T unit. So this would be capital T, this would be 2 capital T, 3 capital T, so on and so forth. For one period, how would I describe this voltage waveform? So V naught over capital T. So that's my slope. What else? Times lowercase t. Do I have any intercept to worry about? No, because it's starting at y is equal to 0 effectively, right? So this is what my voltage waveform looks like over one period, and then a little reset once I hit t and all that, or capital T and all that kind of good stuff. So if I want to find the effective value of this sawtooth wave, I would have V effective is the square root of 1 over t times the integral over exactly one period of v squared of t dt. Again, this is just my generic equation, just so that you guys get used to seeing it. Putting in the parameters for my specific circuit, I would have 1 over t times the integral from 0 to t of v naught over capital T times t, quantity squared dt. Just as a heads up, the most common mistake I see students make when trying to calculate the effective value for any periodic signal is forgetting to square the signal itself, right? We're doing root mean squared, so we absolutely have to remember to square our voltage waveform or our current waveform. All right, so the V naught over T is a constant, so we can actually take that outside of our integration. And so that's going to look like V naught squared divided by T cubed times the integral from 0 to T of T squared dt. What's the integral of T squared? T cubed over 3, right? So we're going to have V naught squared over T cubed times 1/3 of lowercase t cubed evaluated at capital T and 0. I'm going to do this over here. So that's going to look like V naught squared over capital T cubed times capital T cubed over 3 minus 0. Capital T cubed in the numerator cancels capital T cubed in the denominator, and I am left with V naught over the square root of 3. So the effective value for a sawtooth wave is simply the maximum value of the sawtooth wave divided by the square root of 3. So we've looked at rectangular pulses, commonly used in electrical engineering. We've now looked at sawtooth waves, also commonly used in electrical engineering. Let's circle back around to what the hell we're actually talking about, the sinusoidal wave. Okay. So let's say this time, just for the sake of argument, I'm going to say that we're dealing with a current waveform. So let's say that our current is Im cosine of omega t plus some phase angle theta I. And I want to find the effective value of this. So the effective value for a current is the exact same relationship for the effective value of the voltage. We would have 1 over t times the integral from 0 to t of I squared t dt. How do I relate my period capital T to my angular frequency omega for any sinusoid? You had to do it a couple of times in your homework. We definitely went over it in class. 2 pi over capital T. Absolutely right. Okay. So plugging in the parameters for this particular waveform, 1 over t is going to look like omega over 2 pi. I'm going to be integrating from 0 to 2 pi over omega. This is going to be Im cosine omega t plus theta I quantity squared dt. Using trig identities, or actually it's just one identity. We used it yesterday, or Friday, pardon me. This is going to look like 1/2 Im squared plus 1/2 Im squared cosine twice omega t plus twice theta I. I'm going to break this integral up into 2 parts to make it a little easier to deal with. So we're going to have this omega over 2 pi. Our first integral, we're going to have the integral from 0 to 2 pi over omega of just 1/2 Im squared dt. Our second integral, 0 to 2 pi over omega of 1/2 Im squared cosine twice omega t plus twice theta I dt. Close my brackets. So we're about to get to that thing that I told you guys we were going to see it again, and then I expected you all to forget it. So let's see whether or not my prophecy is true. What is the integral of that second term? So I am integrating a cosine function that is oscillating at a frequency of 2 omega over the period for a signal that has an angular frequency of omega. So effectively, I'm integrating this guy over exactly 2 periods. So this whole integral should just be 0. I know Ian remembered he'd been sitting there with a 0 in his hand for the last 2 minutes. But yeah, that whole second term there goes to 0. And so all we have left is this bit on the left. Well, all of that stuff is just a constant, right? So we're going to have the square root of omega over 2 pi times 1/2 Im squared times the integral from 0 to 2 pi over omega of dt. The integral of 2 pi over omega dt is just 2 pi over omega. So this part winds up canceling this part, and all we're left with is the magnitude of our current waveform divided by the square root of 2. So this is a very important relationship. Let me ask you what I hope is a really dumb question. Would it matter if this were a voltage? Would be. Yep, absolutely right. So this works for voltages and currents. Okay, so anytime that we have a sinusoidal voltage or current, the effective value is simply the magnitude divided by the square root of 2. Now, what's really, really great about this is that the result that we got is utterly independent of angular frequency. There is no omega in there whatsoever, which means this is equally valid here in the United States, where we operate at a linear frequency of 60 hertz or an angular frequency of 120 pi radians per second, or in Europe, where they traditionally operate at 50 hertz or 100 radians per second. The effective value is the same everywhere for a sinusoidal signal. It also is independent of phase angle. There is no theta I or theta V or anything in here. So it does not matter when we start measuring or anything like that. Our effective value is simply the magnitude divided by √2. Yes. So AC power distribution was invented in the United States. I couldn't really tell you why we do 60 hertz or 60 cycles per second, and why Europe does 50 hertz or 50 cycles per second. I think it has something to do with just the way that we constructed our generators and all of that kind of good stuff. That being said, like I don't know why the US uses 60 hertz, nor do I know why Europe uses 50 hertz, but I do know why Japan uses both 60 and 50 hertz, and it's because of World War II and who they were occupied and what regions were occupied by what forces after World War II concluded. So actually there is a river through the middle of Japan, their main island, where they have a bunch of frequency conversion stations that convert the 60 hertz power on the side that was US occupied to 50 hertz power on the side that was European occupied, so that their entire grid can be utilized by the whole country instead of having two separate grids. But anyway. Yeah. Yeah. All right. So I want us to look at something real quick. So this is getting into complex power. Let me go, because I forgot to clear my screen or whatever. All right. So I want to talk to you guys a little bit about what complex power is before we start getting into the nitty-gritty. And the short answer is it's entirely made up. It is something that electrical engineers came up with to help quantify the different parts of power that we see in steady state sinusoidal or single phase AC systems. Okay. And it was made up to make the math work and be a more simple representation of the instantaneous power relationships and all that kind of stuff that we've dealt with to this point. So if we look at our average power relationship, P average, we found that this was simply 1/2 VM IM cosine theta V minus theta I for any generic element or network or anything like that, right? Well, we could split that factor of 1/2 up. So we could say that it's really VM over the square root of 2 times IM over the square root of 2 times the cosine of theta V minus theta I, or the effective value of the voltage times the effective value of the current times cosine theta V minus theta I. So this is expressing average power in terms of effective values. But we're going to go one step further, okay? And in order for us to go one step further, I'm going to have to introduce a third domain for us to work in, right? So we've worked in the time domain and saw that the math is terrible and that we don't want to work in the time domain if at all possible. We have worked in the frequency domain, and now we're going to work in what's called the RMS phasor domain. So I'm going to explain how we go from one to the other, all right? So recall that a voltage waveform, V of t, in the time domain is Vm cosine omega t plus some phase angle theta v, right? This is our time domain representation. And it's what we actually have, right? If we were to connect an oscilloscope up to one of our outlets, we would see a signal described like this. Now, in order to make the math easier, we started working in the frequency domain. We represented our voltage with a phasor, where we kept the magnitude, kept the phase angle, and threw everything else away. This was our frequency domain representation. And now we're going to work in the RMS phasor domain. And so I'm going to designate that by, instead of putting just a bar over my value, I'm going to put a tilde over my value to let me know I'm dealing with steady state sinusoidal signals. So that's what I'm going to be dealing with. This is nothing more than my voltage phasor divided by √2, because we know that the effective value for any sinusoidal signal is just taking the magnitude and dividing by √2. So this is going to look like Vm angle theta V divided by √2, which is just Vm over √2 angle theta V, or V effective angle theta V. So this is the RMS frequency domain. And just to repeat things here, we get to the RMS frequency domain simply by taking our phasor voltage and dividing it by √2. So that division only impacts the magnitude. It does not impact the phase angle at all. Okay. So the reason why I'm bringing this up is if we look at our average power relationship here, this is just the real part of the following mathematical operation. Our RMS phasor voltage times the complex conjugate of our RMS phasor current. We call this product S. Our complex power. So effectively, we have gone all the way back around from working in DC circuits to where power is just I times V, to now in a steady state sinusoidal circuit, power is just the conjugate of I times V. So we are effectively back to our simple DC relationships, but now they work for power as well. Okay. So let me scroll down here a little bit. So S, which is a complex number, is our complex power, and it is defined to be the RMS phasor voltage multiplied by the complex conjugate of the RMS phasor current. By the way, the only reason we are using a complex conjugate here is because we're trying to force a negative sign right there, because that's what our average power relationship has, is theta V minus theta I. If it were theta V plus theta I, we wouldn't need that conjugate operation, but unfortunately it is. All right, so this is a trick question. What are the units for complex power? It's not going to be watts, okay? Now, you may be thinking to yourself, how can it not be watts? Because we are multiplying voltage and current, and a volt times an amp is a watt. So, once again, complex power is something that was completely made up. So, electrical engineers made up units for complex power to differentiate it from average power. The unit for complex power is the volt ampere. Dimensionally, it is exactly the same thing as a watt, but we say volt amperes so that we know we're talking about complex power and not average power, which is measured in watts. Okay. So our unit here is the volt ampere. So our complex power is inherently a complex number. So that means we're going to have a rectangular representation and a polar representation. So let's start with our rectangular representation. So we are going to have our effective value for our voltage, times the effective value for our current, times cosine of theta V minus theta I. This whole thing right here is our average power. Average power, which is what we've been dealing with up to this point, is measured in watts. Okay. And then we're also going to have an imaginary part. V effective, I effective, sine theta V minus theta I. The imaginary part here is what's called the reactive power. The units of reactive power, this is another made-up unit, is volt amperes reactive, or VARs. Average power is typically given the symbol capital P. We might also include subscript AVG. We may not, just depends on how squirrely I'm feeling that particular day. And the reactive power is given a symbol Q. So we can express our complex power as simply P plus JQ. Now, I'm putting it to you in this particular form over here because I genuinely do not expect you to ever use the equation for average power, V effective, I effective, cosine theta V minus theta I, or the equation for reactive power, V effective, I effective, sine theta V minus theta I, because if you can just do this simple operation in your calculator using complex numbers and tell your calculator, give me the answer in rectangular form, you know that the real part of that is just the average power, and the imaginary part of that result is just the reactive power. So it is completely and utterly pointless to memorize these equations. The only one you need to memorize is that one, and then just understand what part is the real power and what part is the reactive power. So before we move on to the polar representation, let's talk a little bit about what the average power and the reactive power represent. Okay. So the average power is what we as a consumer pay for. It is the portion of the total complex power that can be used to perform work, or it's the portion that gets converted into heat through resistance and all of that kind of good stuff. So it is the useful power that we consume and pay for when we run our computers, televisions, all that kind of jazz. Reactive power, the imaginary part of the complex power, is what's going on with our energy storage elements, like capacitors and inductors. So effectively, the reactive power is generated, and then it gets sent out to the user, and then gets sent back to the utility. Every cycle, we have half the time we are absorbing it, the other half of the time, the utility is absorbing it, and it just goes back and forth, back and forth, back and forth in perpetuity. So you may ask yourself, well, what is it really doing if it's just getting sent back and forth between the utility and the user? It's temporary energy storage for the grid. Without significant reactive power in our grid, every time multiple people turned on their ovens at the same time or something like that, we would have a blackout, right? So imagine, I think this happened the last time, it was a big soccer tournament, I think, in England. After a soccer game ended, everybody turned on their electric tea kettles at the same time and caused a blackout. Something like this actually happened here in Louisiana. I guess it's probably about 15 years ago. Super Bowl. Do you guys remember the Super Bowl in New Orleans where Beyonce did the halftime show and there was a blackout because nobody gave a shit and they went and they turned on their microwaves to reheat food and stuff like that. When the entire city does that at the same time, it creates an undue stress on the system. The reason why it doesn't happen more often is because we have significant amounts of temporary energy storage in the grid based on all of the induction motors, static VAR, capacitor banks, all that kind of stuff placed throughout the grid to keep it from happening. But it's still possible to push it into a blackout state or a brownout state if we're not careful about things. Okay, so that's what reactive power is. Now let's look at the polar form representation. So we're going to have simply V effective times I effective with an angle of theta V minus theta I. This V effective times I effective has a special name. It's what's called the apparent power. And it is simply the magnitude of the complex power. So it's just the complex power if you throw the phase angle away. Because it's the magnitude of the complex power, it is measured in volt amperes. The apparent power is what design engineers typically design to, because it kind of represents a worst case scenario. And by that, I mean, we're not taking into account any constructive or destructive interference that our phase difference between our voltage and current might do to lower the overall values. This is just effectively the maximum it could ever be, like if the voltage was at its max and the current was at its max at the same time. Okay, so this is how we design systems. If you've ever, well, unlikely that any of you guys have done this, but if your parents have ever tried to size a generator for their home or anything like that, it typically has two ratings. One rating is measured in volt amperes, so you're told the apparent power, and then you're also told the average power. So you're effectively being told how much reactive power your system can handle before your generator no longer functions correctly. This quantity, theta V minus theta I also has a special name. This is what's known as your power factor angle. We'll talk about power factor a little bit today and in a lot of depth on Wednesday. It's an angle, so its unit is just degrees or radians, whatever's convenient. And then in a simplified form, this is simply the magnitude of our complex power S angle theta S. So the symbol for our apparent power is literally just the magnitude of S because that's all that it is. And then the symbol for our power factor, theta, is just theta S. So once again, it is completely and utterly not important to memorize all of these equations. If your calculator is told to give you the answer of V RMS phasor voltage times the conjugate of RMS phasor current. If your calculator gives you the answer in rectangular form, you have access to average power and reactive power. If your calculator gives you the answer in polar form, you have apparent power and the power factor angle. Sorry, I should write angle there. So, and these relationships are summarized in what's called a power triangle. So in a power triangle, our horizontal axis is our real axis, and our vertical axis is our imaginary axis. For some generic complex power S, make sure I'm using the same colors here. Yep. The projection of S onto the real axis is simply P. The projection of S onto the imaginary axis is Q. The length of S is our apparent power, and the angle formed by S with the positive real axis is our power factor angle. So from this simple diagram, we can easily see that S is E plus JQ, or magnitude of S angle theta S. Just reinforcing that all you ever need to know is V times I conjugate. Now, the power triangle can actually tell us a couple of other things as well, okay? So, for example, let's say that theta S is between 0 and 90 degrees. So what does this tell us? Well, it tells us that our load, or whatever is absorbing this power, is inductive, meaning that R is greater than 0, and our reactance is also greater than 0. This also means, and we'll talk about what this means in a minute, our power factor is lagging. I'm going to underline that. So if our power factor angle is positive, effectively, our power factor is lagging, which means our current lags our voltage, exactly what we would expect for an inductive load. If 0 degrees is greater than theta S is greater than negative 90 degrees, effectively if our graph were flipped over the horizontal axis, we would say that our load is capacitive, where R is greater than 0 and X is less than 0. And we would say that our power factor is leading, where I leads V, Again, exactly what we would expect for a capacitive load. So I probably mentioned power factor at this point close to 20 times. So let's go ahead and explain what the hell it is. Okay. So power factor is a way to measure the, let's call it the electrical efficiency of a system. Okay. Mathematically, power factor is defined to be the ratio of the average power to the apparent power, which is nothing more than the cosine of our power factor angle. So let's talk a little bit about why power factor is so important. So I mentioned earlier that average power is what we as consumers pay for. That is what is on our utility bill. Average power multiplied by time is the total amount of energy that we have consumed. That's what we pay for on our utility bill. The apparent power is what the electric utility pays to generate, right? So even though the, let me rephrase this. So the electric utility generates average power for us to consume, but it also has to generate apparent power that gets sent back to them or back and forth between the end user and the utility itself. Well, it costs money to generate that apparent power, or excuse me, that reactive power, right? So it costs money in the form of, well, you might be burning coal to generate that power. It also costs money in the form of you need larger conduct cables, so larger wires in your transmission lines and all that kind of stuff to handle the larger amounts of current magnitudes if your reactive portion of your power is high. So it costs money to generate that reactive power, but the electric utility does not get to charge for it because it goes right back to them. We didn't get to use it for anything useful. So from the power company's standpoint, they typically want the power factor to be above 95% or so. Some places it might be a little less, other places it might be more. I think the highest I've ever heard was like 97.5%, and the lowest I've ever heard of is 90%. But usually they want the system to be pretty darn efficient so that they're not wasting a bunch of money generating power that really doesn't get used for anything. Okay. Just as another quick anecdote here, I think this happened, it was either last year or the year before last. There was a town that in Texas, and their infrastructure was set up to where there was a, I think it was an aluminum foundry in this city that over time went out of business. And in order to effectively fix their power factor problems after this city, after this aluminum foundry went out of business, this city in Texas invited a whole bunch of crypto farmers to come and establish Bitcoin farms and all that kind of jazz. I don't know a whole hell of a lot about that. Why do you think this place did that? Exactly right. So they were increasing the ratio of P to S by allowing a bunch of people to just burn energy farming crypto effectively in order to perform a very odd form of what's called power factor correction for this city's grid. Okay, we'll talk about power factor correction on Wednesday. All right, so we've defined our power factor here, both in terms of average power and apparent power, as well as in terms of our power factor angle. We've talked a little bit about the context. We've talked about leading and lagging power factor up here when we dealt with our power triangle. So I think this is a reasonable place to hit you guys with an example problem. My notes here. All right, so let's say that we have the following circuit. We have a voltage source that is supplying 120 angle 0 degrees volts RMS to the following network. So we have some generic impedance ZA. Here's a generic impedance ZB. Here's a generic impedance ZC. And let's put a current source on this side. Let's make this 5 angle 45 degrees amps RMS. Let's define our impedance ZA to be 10 plus J8 ohms. ZB to be 12 minus J3 ohms. And ZC to be 8 angle 30 degrees ohms. And I want us to find the following quantities. The average power absorbed by impedance ZA, the apparent power absorbed by impedance ZB, the reactive power absorbed by impedance ZC, and the power factor at which the voltage source supplies power. Excuse me, that should be PFVS. And the power factor at which the current source supplies power. So I want to reiterate, I pretty genuinely expect you guys to not memorize literally any of the equations that I've hit you with today. We are simply going to use the complex power fundamental relationship. S is equal to RMS phasor voltage times the complex conjugate of RMS phasor current to figure out damn near everything here, okay? So I am going to define the voltages that we're going to use. So let's call this voltage VA. This will be our phasor current IA. This will be VB. This will be IB. This will be VC. IC. And then while we're at it, I want power factor at which my sources are supplying power. So this is going to be the voltage drop across my current source. And this is going to be the current flowing through my voltage source. All right. So which of these quantities do you all want to solve for first? Because with our current level of understanding, and I say that with some level of foreshadowing, we need to know all of these things. Do what now? Okay. Do you have a suggestion as to how we might do that? Okay, so I'm going to take Walker's suggestion, and I'm going to do nodal. And by that, I actually mean just Kirchhoff's current law at that top middle node with the bottom node as ground. And that'll actually get me one step away from every single one of these quantities. Okay. So if I put my ground here, this nodal voltage is literally the exact same thing as the VB that we need to find anyway. And once I find that, just using algebra, I can figure out everything else pretty easily, right? There's a couple of other things that we could do, but this will be a pretty easy way to do stuff. All right, so applying Kirchhoff's current law at this top middle node, I'm going to have VB minus 120 angle 0 degrees volts RMS divided by my impedance ZA, which is 10 plus J8 ohms, plus my impedance VB, excuse me, my voltage VB, divided by my impedance ZB, which is 12 minus J3 ohms. And then lastly, I can see that I have a current of 5 angle 45 flowing in, so I'll have minus 5 angle 45 degrees amps RMS flowing out and set that equal to 0. Now I am going to reorganize my equation. So I'll have VB by itself over here. 1 over 10 plus J8 plus 1 over 12 minus J3 is equal to 120 angle 0 degrees volts RMS divided by 10 plus J8 plus 5 angle 45 degrees amps RMS. Okay. Now getting my trusty TI calculator because it's the one that I prefer to do complex math on. 1 over 10 plus 8i plus 1 over 12 minus 3i. So this bit right here looks like 0.142 and some change with an angle of negative 11.819 degrees. I'm storing this in my calculator as X. And then all this stuff over here, 120 over 10 plus 8i plus 5 angle 45 degrees looks like 11.097 with an angle of negative 12.057 degrees, and I'm going to store this in my calculator as Y. From this, VB is equal to Y divided by X and I get 77.917 with an angle of negative 0.238 degrees. Volts RMS. So from here, I could say that IB is just VB over CB By the way, I'm storing that as B in my calculator. So IB would be B divided by 12 minus J3. 6.299. Angle 13.798 degrees, amps RMS. And now I can solve part B. So let's do that really quickly. So the complex power absorbed by element B is just my RMS voltage VB times the complex conjugate of my RMS phasor current IB. So that's going to look like B times the conjugate of C, which I get to be 490.813 with an angle of negative 14.036 volt amperes in polar form. Converting that to rectangular gives me 476.158 minus J 119.040 volt ampere. Which of those numbers am I actually interested in? So if we scroll back up here, we were trying to find the apparent power for element B. The apparent power is just the magnitude of our complex power in polar form, right? So I didn't memorize any equations whatsoever. I'm just letting my calculator do the work for me and just taking which parts I need. Okay? The units for this would be in volt amperes, reactive. No, sorry, volt amperes. So $490.813 volt amperes. All right, so now that we have part B done, let's look at part A. So with VB as a known quantity, thank you for your suggestion, Walker. Ian, how would we solve for VA? Exactly right. So VA would just be 120 angle 0 degrees minus VB, which I get to be 42.085 with an angle of 0.440 or 4.1, if I round correctly, degrees, volts RMS. I'm storing that in my calculator as A. IA is simply VA divided by ZA, where ZA was 10 plus J8. So I get to be 3.286 with an angle of negative 38.219 degrees. Amps, RMS. I'm going to store this as T. And For part A then, we know that the complex power absorbed by element A is just VA times IA conjugate. A times the conjugate of T. 138.304 with an angle of 38.660 degrees volt amperes, or in rectangular form, 107.998 plus J 86.398. Which part of this thing am I looking for? So we were asked to find the average power, if memory serves me correctly, which would be the real part of the rectangular representation. So PA would just be 107.998 watts. All right. Before we move on to, I guess, part C here, anybody have any questions about what we've done to this point? So when we're doing nodal analysis, we're just adding current. So I wouldn't multiply and divide by the impedance. I just need the current. Right. So I know that those two elements are in series. So whatever current is being supplied by that source has to be flowing through that element. So I did it that way in order to eliminate having to find a nodal voltage here. Yeah. All right. So how can I find VC or IC? Exactly correct. So Christina suggested that we can find IC is just negative 5 angle 45 degrees amps RMS. So that would look like 5, and then let's subtract 180 from that. So negative 135 degrees amps RMS, which I'm going to store as, I don't think I've used D yet. From this, VC is just IC times ZC, just Ohm's law, where ZC was 8 angle 30. Yep. I get to be 40 angle negative 105 degrees. Volts RMS. I'm going to store this as Y. I don't think I've used Y yet. And then for part C, the complex power absorbed by impedance ZC is just VC times IC conjugate. So that's going to be Y times conjugate of D, which I get to be 200 angle 30 degrees volt amperes in polar form. or 173 plus 0.205 plus J100 in rectangular form. And which part of this am I actually looking for? Right, so I was asked to find the reactive power, which is the imaginary part of our rectangular representation. And so QC is just 100 volt amperes reactive. All right, now let's look at part D. So for part D, I'm trying to find the power factor of my voltage source. So the complex power supplied by my voltage source is going to be 120 angle 0 degrees volts RMS times IA conjugate, because IA is the current flowing into the negative polarity terminal, which is the same as the current I defined as IVS. So 120 times the conjugate of, let's see, IA is stored in my calculator as T. I get 394.356 with an angle of 38.2193, so 219 degrees, volt amperes. How do I get my power factor from this? Just the cosine of the power factor angle. So cosine of the angle of my previous answer is 0.786. Is this power factor leading or lagging? Lagging. Why? Because the angle is positive. Absolutely right. Go away menu thing. Lastly, for part E, how am I going to find the voltage drop across my current source? VB minus VC, absolutely correct. Sorry, I put I. That should definitely be a V there. All right, so let's see. VB is in my calculator as B, if I'm not mistaken. VC is in my calculator as Y. So I get 96.225 with an angle of 23.463 degrees. Volts RMS. The complex power supplied by my current source is going to be the voltage drop across that current source times that 5 angle 45 degrees conjugate. So I'm going to take my previous answer and multiply it by 5 angle negative 45 degrees, which gives me 481.127. with an angle of negative 21.537 degrees volt amperes. My power factor is then the cosine of negative 21.537 degrees. Which I get to be 0.930. Is this power factor leading or lagging? Leading, because the power factor angle is negative. All right, I think this is a good point for me to stop today since we actually only have 15 minutes left of class anyway. So I'm happy to answer any questions that you guys may have. Work on the in-class assignment for the next few minutes, all that kind of good stuff.